Welcome back, Physics 30. This is the section 26-2, Postulates of the Special Theory of Relativity. So the previous example, we looked at some of the results that the Michelson interferometer suggested, and the idea that light travels at a definite speed, no matter what, the frame of reference. So we'll take a look now. The problems that existed at the start of the 20th century with regard to electromagnetic theory and Newtonian mechanics was beautifully resolved by Einstein's introduction to special relativity in 1905. Unaware of that the Michelson morally null result, Einstein was motivated by certain questions regarding electromagnetic theory and light waves. For example, if he asked himself, what would I see if I rode a light beam? The answer was that instead of a traveling electromagnetic wave, he would see alternating electric and magnetic fields at rest whose magnitude changed in space but did not change time. Such fields, he realized, had never been detected and indeed were not consistent with Maxwell's electromagnetic theory. He argued, therefore, that it was unreasonable to think that the speed of light relative to any observer could be reduced to zero, or in fact reduced at all. This idea became the second postulate of his theory of relativity. In his famous 1905 paper, Einstein proposed doing away with the idea of ether and the accompanying assumption of preferred or absolute reference frames of rest. This proposal was embodied in two postulates. The first was an extension of the Galilean-Newtonian relativity principle to include not only the laws of mechanics but also those of the rest of physics, including electricity and magnetism. So the postulates of special theory of relativity. One is the relativity principle. So the first postulate is often called the relativity principle. The laws of physics have the same form in all inertial reference frames. So frames at rest or frames moving with constant velocity. With constant velocity meaning, of course, speed and direction. So the first postulate can also be stated as there is no experiment you can do in any inertial frame to determine if you are at rest or moving uniformly at constant velocity. And the second postulate is the speed of light principle. Light propagates or moves through empty space with a definite speed, which we call little c, independent of the speed or the source or the observer. So it doesn't matter if you're moving or if someone flashes a flashlight on a train, it is always 3.00 times 10 to the 8 meters per second in a vacuum. Now, of course, if it's in air, it's a little bit less, also through glass, through water, etc. But in a vacuum, it stays at that speed. It can slow down in various materials like water, though, is what I further mentioned there. These two postulates form the foundation of Einstein's special theory of relativity. It is called special to distinguish it from its later general theory of relativity, which we'll look at later, which deals with non-inertial or frames that are speeding up or slowing down, accelerating in some fashion, and that we'll look at in chapter 33. The special theory, which is what we discuss here, deals only with inertial frames, frames at rest, or frames moving with constant velocity. Now, the second postulate may seem to be hard to accept because it doesn't matter if we're moving or the source is moving. Light is 3.00 times 10 to the 8 meters per second. First of all, we have to think of light traveling through empty space. Giving up ether is not hard, however, since it had never been detected. But the second postulate tells us that the speed of light in a vacuum is always the same, 3.00 times 10 to the 8 meters per second, no matter what the speed of the observer or the source is. And that's weird because back earlier we talked all about frames of reference here. If you're moving 2 meters per second and the train is moving 10 meters per second, an outside observer sees 2 plus 10, the red shirt dude moving 12 meters per second. They add up. And that here we're talking about the speed of light. If this guy has to shine a flashlight and the light moves 3.00 times 10 to the 8 meters per second, and if the train is moving at a certain speed, you don't add them up. Light is just simply 3.00 times 10 to the 8 meters per second. So that is the weird part of all of this. That second postulate, light travels the same speed in a vacuum, no matter what. So this conflicts with our everyday experience. We would expect to have to add in the velocity of the observer. On the other hand, perhaps we can't expect our everyday experience to be helpful when dealing with high velocity of light. Furthermore, the null result of the Michelson-Morley experiment, which showed that orientating the experiment however you want Speed of light still the same. Einstein's proposal has certain beauty. By doing away with the idea of an absolute frame of reference, it is possible to reconcile classical mechanics with Maxwell's equations. The speed of light predicted by Maxwell's equation is the speed of light in a vacuum in any reference frame. Einstein's theory required us to give up common sense notions of space and time, and the following sections will examine some strange but interesting consequences due to those two postulates there. Our arguments for the most will be simple ones. So on the next page there, we will use a technique that Einstein did himself. We will imagine very simple experimental situations in which little math is needed. In this way, we can see many of the consequences of relativity theory without getting involved in detailed calculations. These are referred to as thought experiments. So whether it's a rocket ship approaching the speed of light or something else, that's what we're going to look like. All right, we'll see you again.